So we're on lesson 20, guys. Lesson 20. We're gonna go 20 and then 19. Yeah. So we are gonna do quite a bit of graphing. We're gonna use our graphing calculators for a lot of it. Sometimes you forget to breathe. You know what I mean? You realize like you're hardly breathing at all. Does that ever happen to you? You gotta remember that breathing is really important.
That's yes.
Alright. And now we can really breathe. Alright. So, you guys have transformed quadratic equations, or quadratic functions, I should say. You should have in Algebra 1. You have also transformed linear equations, linear functions, okay? We're going to use what we know about that to transform logarithmic and exponential functions. Additionally, you should have looked at exponential functions at some point in time during Algebra 1 as well. So we're going to use a lot of the tools that you learned in there, and I'm going to have to probably refresh you a little bit on those because it's been a little complicated. So, well, let's go ahead and first graph. Let's graph x squared. All right, x squared. Remember. Whoa. We can do a table of values for this. Right, when I graph I like to choose some really easy values to plug in. And f of x in this case is x squared, right? So, when x is negative 2, f of x, or y, is 4. When x is negative 1, right, I'm plugging negative 1 in for x in x squared, right? So negative 1 times negative 1 is positive 1. 0 times 0 is 0. And then we get a reflection, right? Let's go ahead and plot those points. Negative 1, 1, positive 1, 1. We've got a point here at 2, 2. 2, 2. And then we've also got a point, oh my god. 2, 4. Sorry about that. I was making an absolute value function, so 2, 4. 2, 4. Alright. So that's approximately what that thing looks like. If you want to double check it, just put it in your calculator. Y equals x squared? Yes.
Do you want like the table of square calculator? We plug that sort of table right there into a calculator and graph out of it.
You can. It's not super helpful.
So it's better just to do it.
Not for this stuff, yeah. What is pretty cool is that you can get the table of values after you put in the graph. And that's kind of nice. I'm going to show you how to do that today. So now we're supposed to, so we graphed this one, we need to graph this one. Let's look at that though, g of x. If we use our properties of exponents, isn't that the same thing as 2 squared times x squared plus 1? Which turns out to be 4x squared plus 1. Which, hey, what the heck? That's the same thing as h of x. So hey, if I graph g of x, then it looks like I also graph h of x, right? It's the same. Okay. Okay. So let's go ahead and graph that one, okay? So what we're doing is we're plugging in all of those same values for that x right there. So what happens when x is -2? So let's do that over here. So we have x, and then we have, we'll just go ahead and call it g of x, why not? So if I plug -2 again in right there, -2 times -2 is 4. So 4 times 4 is 16, plus 1 is 17, right? -1, if I plug -1 in there, -1 times -1 is +1, times 4 is 4 plus 1 is 5. Just do that in my head there, okay? How about 0? 1, right? Because I have a 1 here. And then we know that because it's a parabola, it's going to just reflect, right? Let's go ahead and graph it. -2, 17. And we know it's going to be reflected right there as well. All right. And then we're at -1, 5. And then we're at 0, 1. So here we go. Okay. Zero, 0 for this one. Why are we at 0, 1? Yeah, this is this one. Okay. What happened? What happened? You guys remember? I don't know if you remember. Maybe you do from Algebra 1. That this is going to be a horizontal scaling. Some people call it a squeeze. Right? Yeah. Some people will refer to that as a squeeze. Okay. Remember, when we've got a 1 on the outside like that, this thing here is going to be a vertical translation. Remember, now we're just going back to geometry, right? What is it? It's +1, right? Yeah. Huh? Right. We already explained why T and H are equivalent. And then, hey, you know what's going to happen here? Not that. And you know what else we're not going to do?
Let's just skip it altogether.
You know what else we're not going to do? Let's move on to graphing a logarithm. Okay, so we got log base 2 of x. All right. Let's graph this. And actually, let's go back real quick. And let's graph those other ones using our graphing. All right, so real quick, let's do a little exploration. All right. We're going to explore with our calculators a lot. We'll kind of diverge from this lesson because I feel like a really quick way to learn what's going on with transformations is put the different stuff in your calculator, see what happens, right? So x squared is something we're really familiar with, okay? So let's look at x squared and graph it. And hey, it looks a lot like our x squared that we graphed. Okay. What happens when we do x squared plus 1? Put it in your calculator. Dang it. Dang it. Looks like I take the same graph and shift it up 1, right? Okay, all right. So we did that. Let's see what happens if let's go ahead and clear this one. What happens if I put a 4 in front? A coefficient of 4. Looks like it squeezes it, right? It squeezes it horizontally. Yeah? Alright. And this is just a refresher. You guys have seen all this stuff happen. What if I make this 1/4 instead of 4? What's going to happen then? Let's see.
Oh, great.
It says, what are you doing? Oh, I forgot a parenthesis here. It stretches it out, right? Well, before we get started, let's look at logarithms. Let's look and see what happens when before we get into the lesson. Let's look at what happens when we do this to all of our different logarithms, okay? So let's go ahead and graph log of x, log base 10 of x. That's what it looks like, and remember, it keeps going down, down, down. Remember, this, as x approaches 0, y, or f of x, approaches negative infinity, right? So it keeps going down forever and ever and ever. What happens if I do the same thing and I add 1, just like we did with our, x squared? It shifts it up, yes. It shifted it up, right? So, That was interesting. All right, what happens if I multiply it by 4?
No, I was trying to save my hair out of the mouth.
Ooh. That was a stretch, right? So it looks like we took this one and we went like that, right? We stretched it.
So like when you add numbers to the end of it, it's like a log, the base, no, not the log base, but not like the log base.
Yeah, and then you have a number after all that.
Yeah, the number after all that, that's going to raise it.
It's going to shift it either up or down.
For the logarithm. Something. What does it do in terms of
It stretches it out. Yeah, if we're multiplying it, it's like we're stretching it. We're gonna see that. We're gonna graph a few. But I just wanted to do a quick comparison real quick. And then go ahead and look at the lesson. All right, so let's go ahead and graph this. All right, let's graph this thing. All right, we have a point at 1/4, somewhere around here, -2, so something like that. And then we have a point at 1/2, -1. Something like that, and then we've got a point at 1 what? Okay, we gotta plug these in. We're plugging in these values in here. Log base 2 of 1 is what? We're saying 2 to what power is 1? 0. So if we're plugging the 2 in there, log base 2 of 2. 2 to what power is 2? And 2 to what power is 4? And then that makes sense that would be 3. So we're going to continue to graph it.
So we can treat the log base 2 of x as sort of f of x.
It is f. Whatever you get when you plug in x.
Oh, I see.
Yeah.
That makes sense.
Okay. So we got the point 1, 0, 2, 1, 4, 2, 8, 3, and then, I mean, we can keep going, right? What's 16 going to be at? All right. Something like that. Of course, my drawings aren't always that great, but sometimes math is good reasoning from bad drawings. What happened? What's up? What's confusing?
Okay, so like when you're graphing, what if it's negative, what if it's
If it's negative light. So I'm putting in positive x values and it spits out a negative y value. So I'm going to show you a trick to fill in these tables from a function. Unfortunately, I have log base 2, right? So in order to do it on every single calculator, I have to change the base like we've been doing before, right? So log base 2 of x is the same thing as log base 10 of x over log base 10 of 2, right? I'm going to put that in my calculator. You can use the log base function if you have it on your calculator. So we'll graph it using our calculator. Again, I said we needed to graph that. If you have this log base, go ahead and use it. I'm not going to use it because not everybody can use it. So I'm going to do this as log of x divided by log of 2, right? That's the way to change it. Then I hit graph, and it should look a lot like what we just graphed. It does. Fantastic. There is a cool thing that you can do, and I can't see it because you can hit second and graph, and it gives you that table.
Wow. Really? Why didn't
Huh? Why didn't I tell you about it earlier? I don't know.
I realized we don't have to do that stupid little trace button where you like try and line it up.
Oh, you can do that too, but no, but trace you can enter. Okay, I get it. Yeah, you can enter different values for trace as well.
So you can.
Yeah.
Well, this one is just like straight up. Like everything.
And you can go up, and it gives you all these. Why does it say error for all of those x values? There's no such thing, right? Yeah. Yep. It's not giving you the fraction values though, right? If you wanted to get those fraction values, you would have to go to your graph, and you would have to hit trace. And then if you wanted to know the value at, say, 1/8, right? You can just, when you're there, you can hit 1 divided by 8, and it's telling you, you're telling it, hey, tell me what the y value is of this for an x value of 1/8. I'm going to give you -3. Okay? So there are a few different ways to get these values. If you needed to fill in a table of values, or if you had something missing like you were asking about, that would be the way to do it.
Thank you.
You are welcome. All right. I believe that finishes that page. Eureka's trying to be tricky here. We're like, what? 8x? You didn't tell us what happens when we have something multiplying the x, but it turns out that we have a property of logarithms that allows me to split those up into 2 logarithms, right? Yeah. We have a product. We have a product inside of our logarithm. So that'll be log base 2 of 8. Can't I write that as sum now? Log base 2 of x, right? Right, since that says 8 times x in the parentheses, I can write that as log base 2 of 8 plus log base 2 of x. And what is log base 2 of 8? 2 to what power is 8? Trey? So, then it turns out that this is 3 plus log base 2 of x, which is q of x. So what's the sequence of transformations? We already said this right here is a vertical translation, right? And that's it, right? It's going to be up 3. We already determined that h of x and g of x are the same, right? So let's go ahead and graph these things. We already have the table filled in for f of x, right? That's on the previous page. -2, -1, 0, 1, 2, 3, right? I'm going to argue that all we got to do is add 3 to our y values, right? Think about it. If we're taking a thing and we're shifting it up, every point gets shifted up 3, right? And can't I just add 3 to my y values? I'm going to do it, and then I'm going to show you when we graph it that that's definitely true. So if I add 3 here, I wind up with 1, 2, 3, 4, 5, 6. Counting's good. Oh, I missed the opportunity to go. 1, 2, 3. Oh, 3 balloons! 3 is the number of the day! Well, Count Dracula from Sesame Street? Sesame Street? Okay. Well, we're not worried about h of x, because h of x and g of x are the same. Alright, rather than graphing these here, I'm going to put them on my handy dandy graphing calculator. I already have that one there, right? No, that one is the equivalent of log base 2 of x. So we need log base 2 of x plus 3, yeah? Yeah. So log base 10 of x divided by log base 10 of 2 is the same thing as log base 2 of x. I gotta change that base if I'm gonna put it into every single calculator. And then all we're gonna do is we're gonna add 3 and see what happens when we graph it.
Whoa.
What happened? It shifted it up 3. And I'm going to now argue to you why I was able to just add 3, right? Check it out. This one has the coordinates of 1, 0, right? What are the coordinates of this one at, if I was to go up at 1, it looks like this has the coordinates 1 and 3, right? And you'll be able to see that they match. At 2, we're at 1 here, right? But if we go up 3 here, we're at 2, 4 for this one. You see why I was able to add 3 now? We're just adding 3. This distance is 3, this distance is 3, and so on. Okay? Yeah.
I try to plug in my calculator. I don't know what I'm writing down.
If you want to, you can jot these graphs here. You should. Sorry, not if you want to. Please. I'll do it. I know that it has points here. Here, yes. And then I can just estimate these other points. And it'll still look real nice. Right? And then all I have to do to find my other points is just add 3. I can go 1, 2, 3, boom. I have another point here at 4, so I can go 1, 2, 3, bam. I have another point here at 8, and I can go 1, 2, 3, boom. And then at 16, we have another point 1, 2, 3, right there. Oh. And then I can, right. There, we did it. We've done it. Yay.
Look at the other point. So,
Huh?
why is that one point on like -1, -1? Graph.
-1, -1?
You transform graph.
It's at the point like 1 something. It's an estimate. It's not perfect. Yeah. but I think it's almost right, actually. At 1. Okay. Moving on. Let's do more, because more is better. We already did this. We showed a property to show the 8 are equivalent right away, because that bothered me right off the bat. How about this one? We got another one that we're going to be able to show if they're equivalent. That we are going to be able to show if they are equivalent. Because again, I can see that I can use the property of logarithms in there, right? Yeah. It is true that p of x, if that's log base 2 of x over 4, I can write that using properties of logarithms. That is log base 2 of x minus log base 2 of 4, which turns out to be log base 2 of x minus 2 to what power is 4? What do you think is going to happen to this? If adding 3 brought it up, this should be a vertical translation. Heck yeah. Oh, well. Translation of -2 or what? Down. 2. Yeah? Alright. And when it says describe it as a scaling, what we're going to do is do what we've been saying before. Because of this is a vertical translation. And it's going to be plus 3, or of 3. I like to say in the positive direction rather than saying up or down. It's more. Right?
So you know if it's a vertical or horizontal translation?
We have not yet dealt with the horizontal translation. We're going to do it actually when we pick up next time, because I don't have time to start eyes immediately.